two Lambda functions running the exact same code under the same limit. One of them sails through the traffic, while the other starts throwing errors and throttle. And the only difference between them is how each one is getting called. And by the end of this video, it will make complete sense. So let's get started.
Concurrency is the word everything in this video builds on. So let's get it right. When a request arrives, Lambda runs your code inside a small box called an execution environment. That box handles one request at a time, and while it's busy, nothing else can use it. The moment it finishes, Lambda keeps it warm and hands it to the next request instead of throwing it away. Picture 10 requests landing at almost the same moment. One box cannot keep up, so Lambda spins up more, one for each request that needs serving right then. Your concurrency is how many of those boxes are busy at the same instant. Freeze any moment, count the busy boxes, and that's the number. One formula makes all of this predictable. Your concurrency equals requests per second times how long each request takes in second. Say 100 requests comes in every second, and each one takes half a second to finish. 100 times 0.5 is 50. So you need 50 environments running at once. Watch what happens when you change the inputs. Double the traffic to 200 requests a second, but make each request twice as fast. A quarter of a second. That still works out to 50. You get twice the traffic at the same concurrency, because a faster function needs fewer environments to carry the same load. Scale it all the way up and the math still holds. 5,000 requests a second at 200 milliseconds each works out to 1,000 environments, a number worth remembering as we turn to limits. That 1,000 is a real limit, and it's shared. By default, every AWS account gets one pool of 1,000 concurrency execution per region. Every function you run in that region pulls from the same pool, so they are all competing for the same 1,000. When pool runs dry, the next request gets turned away, and that's what throttling means. Two things to know about that number. It's a default, so you can ask AWS to raise it whenever you need to. And Lambda always keeps 100 units of the pool aside for functions that haven't reserved any concurrency of their own. The limit you just saw count concurrent executions, not requests per second. To get from one to another, you multiply by how long the function runs. Concurrency equals requests per second times duration in seconds. That multiplier is what the surprise height. Picture 20,000 requests a second hitting two functions. If each one runs for a full second, that's 20,000 environments at once. 20 times the default limit, so most of it gets throttled. Make the function fast instead. 20 milliseconds each. And those same 20,000 requests only ever occupy 400 environments at any instant. Nowhere near the ceiling. The traffic is identical, but the outcome is the opposite, which is why the requests per second number on its own cannot tell you whether you will be throttled. You have to multiply by duration first. The limit tells you how many concurrency you can have. How fast you can get there is a separate rule. Each function can add up to 1,000 new environment every 10 seconds, and that speed limit applies to each function on its own. One function scaling harder doesn't slow another one down. There is where a lot of surprise throttling comes from. If a sudden spike asks for a 5,000 environment right now, Lambda cannot create them all at once. It climbs toward that number 10 seconds at a time. And any request arriving faster than it can scale get turned with a 429 stats code. Even when you are nowhere near the 1,000 ceiling, you can get throttled for scaling too quickly, not for hitting the cap. This per function speed limit is fairly recent. AWS shipped it at the end of 2023, and it made functions scale roughly 12 times faster than the old shared burst model it replaced. So far, it's been about how Lambda counts concurrency and how fast it scales. What actually changes the behavior you see is how your function gets invoked. And there are three ways in. A caller can invoke it and wait for the result. A caller can hand off an event and walk away. Or Lambda can go and pull the work from a source itself. The first two are push models, where the caller pushes work at Lambda. The third is a pull model, where Lambda reaches out and grabs the work. That split, push versus pull, runs through the rest of the video because each path handles a spike in its own way. Start with synchronous model, the most direct one. The caller invokes your function and holds the line until it returns an answer. API gateway in front of a REST endpoint is the classic example. Every caller waiting on a response is one busy environment. So your concurrency here is the number of requests in flight at that moment. Because the caller is waiting, there is nowhere to hide backlog. When you run out of concurrency, Lambda hands the caller a 429 error right then, and it's on the caller to retry or to show the users a failure. This is the least forgiving model. Nothing absorbs the spike for you. So the synchronous path is where throttling is most visible to the people using your app. The asynchronous model works differently. You hand Lambda an event and it immediately replies with a 202, meaning got it. Before your function has run a role, services like S3 and SNS and Event Bridge invoke functions this way. Behind the scenes, Lambda drops your event into an internal queue that it owns and manages for you. A separate processor inside Lambda reads from the queue and invokes your function. How many runs at once is Lambda's call. It scales the execution up to match the backlog at the standard scaling rate and caps them at your concurrency limit. Under pressure, that buffer is what saves you. If you are being throttled, the events wait in the queue and get retried instead of failing in front of the caller. So it observes the spike the synchronous path couldn't. If your function errors out, Lambda retries it a couple of times, and it will hold events for hours before giving up. When something finally cannot be processed, you can route it to a dead letter queue or an on failure destination so nothing is silently lost. The third model is pull based, and it flips the direction. Instead of something calling your function, Lambda runs its own puller that reaches into a source. Pull a patch of records and invoke your function with that patch. You connect the two with a small piece of config called an event source mapping, and Lambda handles the pulling for you. This is how Lambda works with queues and streams, SQS, Kinesis, DynamoDB streams, Kafka, and a few others. Your function gets a patch when one of three things happens first. It gathers enough records, a time window closes, or it reaches 6 megabytes. One catch worth remembering is that these sources delivery at least once. So a record can show up twice and your code needs to handle that. From here, the behavior splits two ways, streams and queues, and they scale concurrency very differently. Streams first, like Kinesis or DynamoDB streams. A stream is split into shards, where each shard is an ordered slice of your data. By default, Lambda runs one patch at a time per shard, so your concurrency is tied to your shard count. 10 shards mean up to 10 invocation at once. When one Lambda per shard isn't enough, there is a setting called the parallelization factor. Raise it from 1 up to 10, and Lambda run that many invocation on a single shard. So 10 shard at a factor of 10 give you up to 100 at once. Even then, records with the same partition key stays in order. The ordering has a cost. If your function keeps failing on a patch, Lambda pauses that shard until the patch succeeds or the records age out, rather than skip ahead and break the order. So one stuck record can hold up its whole shard, which is another reason to spread work across more shards. It shrinks the damage when one gets stuck. The parallelization factor is worth slowing down on because it's where people get lost. Say your partition key is a user ID, and one shard carries a mix of users all interleaved. At a factor of 1, a single invocation walks through the shard a patch at a time, with every user's events jumbled together in arrival order. Raise the factor and Lambda groups the records by key. Everything for the user 42 goes into one invocation, user 17 to another. A user's events stay in their original order, so a checkout never runs ahead of its add to cart, while different users processes in parallel. That's how a single shard can deliver up to 10 invocation at once. Quick note on how Lambda reads a stream, because there are two ways. The default, called the standard iterator, pulls each shard about once a second and shares the shard's read throughput with any other consumers. For most workloads, that's perfectly fine. When you need lower latency, you switch on enhanced fanout. Each consumer gets its own dedicated pipeline to every shard, and records are pushed to Lambda over a long lived connection instead of pulled. This changes how fast and how freshly records arrive, not how much concurrency you get. The shard math from a moment ago still decides that. Queues behave differently from streams. With SQS, Lambda doesn't pin concurrency to a fixed number like shards. It ramps with the load. When messages arrive, it starts with 5 functions running in parallel, and if the backlog keeps growing, it adds a few hundred more each minute until it tops out around 1250 by default. Because it can climb that high, you usually want a guardrail. A maximum concurrency setting on the event source caps how many functions one queue can use. So a busy queue cannot eat your whole account pool and starve everything else. On a FIFO queue, there's a natural cap too, since concurrency cannot exceed your number of message groups. By default, Lambda manages all that polling for you. If you need it to scale faster, there's a newer provisioned mode where you set a floor and ceiling for dedicated poolers for latency sensitive work. For most teams, the default ramp is all you will touch. You have seen each model its concurrency. The last piece is the two knobs for controlling it, and the first is reserved concurrency. It fences off a slice of your account pool for one function. Give a function 400 and 400 is carved out just for it, while everything else shares what's left. The fence works both ways. It guarantees the function can always reach its 400, so a noisy neighbor cannot starve it. And it caps the function at 400, so even if the rest of the pool is ideal, it throttles the moment it tries to go past its own limit. You reach for it to protect a critical function, or a box in one that tends to run away. Two quick facts. Reserving is free, but it does count against your account pool. So what you fence off, other cannot touch. And setting a function reserved concurrency to 0 switches it off, which makes a handy emergency stop. Before the second knob, you need one idea. The cold start. When Lambda spins up a new environment, it has to set it up first. It downloads your code, starts the runtime, and runs any initialization outside your handler. That whole setup is the init phase, and only when it finishes does your function code run. In the invoke phase. The init phase is the cold start, and it adds latency to the first request an environment handles. Once the environment is warm, later requests skip init and run, which is why a warm function fills instant and the cold one lags. For most workload, it's a blip. For a latency-sensitive API, it's exactly what you want to remove. That's exactly what provision concurrency does. You tell the Lambda to keep a set number of environment warm and ready before any traffic arrives. Set it to 200, and 200 environments are already initialized, so the first 200 concurrent requests skip the cold start and response right away. Go past what you provisioned, and what happens depends on your other settings. If you haven't set reserved concurrency, the extra requests pile into normal on-demand environments, and those can cold start again. And these warm environments aren't free. Unlike reserved concurrency, provision concurrency charges you to keep them alive whether they are busy or not. So the two knobs play different rules. Reserved concurrency is free and shapes how the pool gets divided. Provision concurrency costs money and buys warm, instant capacity for the traffic you can see coming. There is where it all comes together. Picture the exact same throttle hitting your function across the four ways it gets invoked. Same code, same limit, and watch how differently each one reacts. Invoke it synchronously and the caller gets a 428 on the spot and has to handle it themselves. Invoke it asynchronously and the event waits in Lambda internal queue and retries, so the caller never notices. With a stream, the affected shard pauses and holds its order until it can move on. With a queue, the messages go back and get picked up again a moment later. That's the answer to the two functions from the very start. The code matched, but how each one was invoked decide everything about how it held up under pressure. Once you know which model you are on, the way Lambda scales and where it throttle stop being a mystery and becomes something you can plan for. Here's the whole model in one breath. Concurrency is requests per second times duration, all drawing from one shared pool with a ceiling and the scaling speed limit. How your function is invoked decides what happens when the pool runs dry. The caller eats the error. A buffer absorbs it, a shared pauses, or messages wait their turn. If this made Lambda concurrency click, do me a favor, like the video, subscribe for more deep dives, and leave comment with the part that finally landed. Thank you for watching.